Listen closely to the silence of space. It is not truly silent at all. In 1977, a radio telescope in Ohio heard something that shattered the quiet, a burst of sound so powerful, so unexpected, that the astronomer who discovered it circled the printout and wrote a single, awestruck word in the margin: "Wow." That signal, blazing from the depths of the cosmos for a mere 72 seconds, was never heard again. It was a ghost in the machine of the universe, a tantalizing whisper that challenged everything we thought we knew. It's a reminder that our universe is not a still and empty void, but a dynamic, buzzing symphony of transmissions, filled with sounds we are only just beginning to hear. We are surrounded by enigmatic cosmic signals, cryptic messages from the farthest reaches of existence that defy simple explanation and ignite our deepest curiosities. These are not just random bursts of energy, they are cosmic puzzles, each one a unique fingerprint left by events of almost unimaginable power. Some are fleeting, appearing once and vanishing forever into the static, leaving behind only a trail of questions. Others repeat with a strange, almost rhythmic regularity, patterns that seem to hint at something more than mere natural chaos. They challenge the very laws of physics as we understand them, suggesting forces and phenomena we have yet to even name. Are we listening to the death cries of ancient stars, the collapse of distant black holes, or could it be something else entirely? This journey into the unknown is not just about cataloging strange sounds. It is a quest to understand our place in a cosmos that is far stranger and far more active than we ever dreamed. So prepare to tune your mind to the frequency of the extraordinary. In this video, we will embark on a journey through 25 of the most baffling and mysterious signals ever detected. We will explore repeating fast radio bursts that traverse billions of light years, signals from seemingly empty space that pulse with clockwork precision, and whispers from the dark that carry an almost artificial signature. Each one is a story, a piece of a grander cosmic mystery waiting to be solved. This is an invitation to look up at the night sky and hear it not as a silent canvas, but as a conversation we are only just beginning to understand. Let's begin. Our journey into the cosmic unknown begins with a signal so legendary. Its name alone conveys a sense of stunned discovery, the wow signal. It all started on a seemingly ordinary night, August 15, 1977, at the Big Ear Radio Telescope in Delaware, Ohio. This massive instrument was part of the Ohio State University's search for extraterrestrial intelligence project, silently scanning the heavens, methodically listening for any sign that we are not alone. For 35 long years, the search had yielded nothing but background static. But on that night, everything changed. The telescope's computer was printing out columns of alphanumeric characters, each representing the intensity of the radio signals it was receiving. Most of the time, the printouts were a boring sea of ones and twos, the cosmic equivalent of radio silence. But then, for just 72 seconds, the printer came alive with a sequence that was anything but ordinary, 6EQUJ5. To understand why this string of letters and numbers was so shocking, you have to know what it meant. The system used numbers 1 through 9, and then the letters A through Z to represent increasingly powerful signal strength. A 1 was barely a whisper, a Z would be an ear-splitting shout. What the Big Ear detected was a signal that rose rapidly in intensity, peaked at a value represented by the letter U, a level of strength 30 times louder than the background noise of deep space, and then faded away just as quickly. It was a perfect, compact burst. The astronomer on duty, Jerry Amon, was reviewing the data printout a few days later when his eyes fell upon this incredible sequence. He was so astonished by the sheer power and perfection of the signal that he circled it in red pen, and in the margin simply wrote, "Wow." That single emotional word gave the signal its immortal name. What makes the WOW signal so compelling and so frustrating for scientists are its specific characteristics. It was observed at a frequency of 1420 MHz. This is no random number, it's a special place on the radio dial known as the hydrogen line. Hydrogen is the most common element in the universe, and scientists had long speculated that any advanced civilization trying to announce its presence might use this universal frequency as a natural cosmic hailing channel. The fact that the WOW signal appeared exactly there is what elevates it from a simple anomaly to a profound candidate. Furthermore, the signal was narrowband, meaning it was concentrated on one very specific frequency, much like a radio station you tune into on your car stereo. Natural cosmic objects like pulsars or quasars typically broadcast over a wide range of frequencies. This narrowband quality is exactly what theorists predicted an artificial signal would look like. And then it was gone. The most haunting aspect of the WOW signal is its singularity. Despite decades of dedicated searches pointed at the same patch of sky in the constellation Sagittarius, it has never been heard again. It was a one-time event, a cosmic shout that echoed for a minute and 12 seconds and then fell silent forever. This fleeting nature has fueled endless debate. Could it have been a reflection of a human-made satellite? Detailed analysis has ruled out any known satellite or aircraft. Was it a natural phenomenon we simply don't understand? Perhaps, but no known natural event replicates all of its peculiar traits. The WOW signal remains the ultimate cosmic ghost, a perfect whisper from the void that continues to defy explanation, standing as a monument to both the promise and the profound mystery of the universe. While the WOW signal stands as a solitary, enigmatic event, the cosmos had another, even more explosive surprise in store, one that would reveal an entire class of cosmic transients. Fast radio bursts are, in many ways, the WOW signal's dramatic successors. They are not faint whispers but titanic, millisecond-long screams of energy that flash across the universe. Imagine compressing the entire energy output of our Sun over a period of 80 years into a single, blinding flash that lasts for less than the blink of an eye. That is the staggering power of a typical fast radio burst, a force so immense it can travel billions of light years and still be detected by our relatively small telescopes here on Earth. These are not slow, building waves of energy. They are sudden, violent spikes in the radio spectrum, appearing from random directions in the sky and then vanishing almost as quickly as they arrive. The story of their discovery is a classic tale of scientific serendipity. In 2007, a young astronomer named Duncan Lorimer was reviewing archival data from the Parkes Radio Telescope in Australia, often called the Dish, which was originally collected in 2001. He was searching for new pulsars, the regular spinning corpses of dead stars, but buried within the terabytes of old observations was something that didn't fit any known pattern. It was a single, tremendous burst of radio waves, lasting a mere 5 milliseconds. The signal was so strong and so brief that Lorimer and his student initially doubted its cosmic origin. The first assumption was that it must be some form of local interference, perhaps a glitch from an electronic device on site, or even a signal bouncing off a passing airplane or satellite. For years, the astronomy community debated the Lorimer burst, with many dismissing it as an anomaly, a ghost in the machine. Confirming that such a brief, powerful signal could come from beyond our galaxy was a monumental challenge. It took the discovery of several more of these bursts by other telescopes around the world to finally convince skeptics that fast radio bursts were indeed a real and profoundly important astrophysical phenomenon. What makes these bursts so useful to astronomers beyond their raw power is a subtle characteristic known as dispersion. As a fast radio burst travels across the vast, nearly empty intergalactic space, it interacts with traces of free electrons. This interaction causes the higher frequency waves to arrive at our telescopes just a fraction of a second before the lower frequency waves. The degree of this delay is a direct measure of how much material the signal has traveled through. It acts like a cosmic mile marker, allowing scientists to estimate not just the incredible distance the burst has traveled, often billions of light years, but also to weigh the invisible matter scattered between galaxies. In this way, these mysterious flashes are doing double duty. They are both profound puzzles in themselves and powerful new tools for mapping the otherwise invisible structure of the universe. Yet for all their utility, their ultimate source remains one of the most heated debates in modern astrophysics, leading us to an even stranger subset of these cosmic explosions. This fundamental distinction between one-time events and repeating signals completely reshaped the scientific investigation into fast radio bursts. For years, the prevailing mystery was how any single cosmic event could possibly produce such an immense release of energy in a mere instant. The discovery that at least some of these bursts could happen again and again from the same location forced a dramatic shift in thinking. It meant that the source couldn't be something that destroys itself in a final, cataclysmic explosion, like the collision of two neutron stars. Instead, the source of a repeater had to be a persistent object, something capable of producing multiple, incredibly powerful outbursts over time. This realization turned a puzzling anomaly into a tangible, ongoing phenomenon that astronomers could aim their telescopes at, hoping to catch it in the act over and over again. The breakthrough came with FRB 121102, discovered in 2012 and confirmed as a repeater in 2015. This object became an instant celebrity in the astronomy world. For the first time, researchers weren't just chasing a ghost, they had a target. The ability to predict, or at least anticipate, further bursts from this source allowed for an unprecedented campaign of observation. The world's most powerful radio telescopes were trained on its coordinates, and in a historic feat, the Very Large Array in New Mexico managed to pinpoint its location with astonishing precision. The signal was traced not to a massive spiral galaxy like our own Milky Way, but to a tiny, unassuming dwarf galaxy more than 3 billion light-years away. This was a crucial clue. Dwarf galaxies are known to be relatively primitive, filled with younger stars and the raw materials for star formation. This environment suggested that whatever was producing these powerful bursts might be linked to the energetic, sometimes violent, processes associated with young stellar objects. The existence of repeaters like FRB 121102 strongly points toward sources that are not just persistent, but also sporadically active. The leading candidate is a type of exotic neutron star known as a magnetar. Imagine the core of a giant star collapsing into a city-sized ball so dense that a single teaspoon of its material would weigh billions of tons. Now add an unimaginably powerful magnetic field, trillions of times stronger than Earth. These magnetars are cosmic powerhouses, and starquakes on their surfaces, cracks in their incredibly rigid crusts, could theoretically unleash titanic shocks, releasing the colossal amount of energy we see as a fast radio burst. Since a magnetar doesn't destroy itself in this process, it could produce multiple bursts over many years, perfectly matching the behavior of a repeater. The dwarf galaxy environment supports this idea, as it's the kind of place where such young, volatile neutron stars could be formed. In stark contrast, the majority of fast radio bursts detected so far are one-off events. They scream into existence from a random point in the sky and are never heard from again. This suggests a different, more final class of cosmic catastrophe. The prime suspects for these non-repeating bursts are cataclysmic events where the source is irrevocably changed or destroyed. The collision of two ultra-dense neutron stars, or the final, death spiral plunge of a neutron star into a black hole, are leading contenders. These mergers would unleash a staggering amount of energy in a single, definitive burst, consistent with a one-off detection. The fact that we see both repeaters and one-offs tells us that fast radio bursts are not a single phenomenon, but rather a final, observable effect produced by several different and equally dramatic cosmic engines. This duality deepens the mystery, revealing a universe that communicates its most violent events through both recurring warnings and solitary final shouts. While the search for fast radio bursts pushes the boundaries of intergalactic astronomy, another project turned its gaze much closer to home, aiming its instruments at the very star next door. In late 2020, the scientific world buzzed with electrifying news. A candidate signal, seemingly from the direction of Proxima Centauri, had been detected. This wasn't just any star. Located a mere 4.2 light-years away, Proxima Centauri is our Sun's closest stellar neighbor, and astronomers had already discovered at least one rocky, Earth-sized planet orbiting within its habitable zone, the region where temperatures could allow for liquid water to exist. The idea of a signal from a potentially life-friendly world right on our cosmic doorstep was almost too thrilling to believe. The detection was made by the Parkes Radio Telescope in Australia as part of the ambitious Breakthrough Listen initiative, a decade-long, $100 million effort to conduct the most comprehensive search for intelligent life beyond Earth ever undertaken. The signal itself, designated BLC-1, which stands for Breakthrough Listen Candidate 1, was everything scientists had been hoping to find. It was a narrowband signal concentrated at 982 MHz, a quiet part of the radio spectrum generally free from human-made transmissions and satellite communications. This narrowband characteristic is a key fingerprint of potential artificial origin. Natural cosmic objects typically emit a much broader, messier splash of frequencies. Even more compelling was its drift rate, the subtle shift in frequency over time. As a transmitter on a distant planet would move relative to our telescopes, its signal would experience a Doppler shift, much like the change in pitch of a passing ambulance siren. The drift rate of BLC-1 was consistent with what you would expect from a transmitter located on a planet orbiting Proxima Centauri. For a moment, it seemed to tick all the boxes of a true technosignature, a potential hello from our closest celestial neighbors. The initial discovery sparked a flurry of excitement and intense scrutiny. The signal was detected during 26 separate observations over a period of several hours, but it was never heard again despite repeated attempts. This fleeting nature itself was suspicious. The subsequent investigation, detailed in 2 studies published in the journal Nature Astronomy, revealed the immense challenges of modern SETI. The researchers meticulously followed a trail of clues, and it led them back to Earth. The most probable explanation, they concluded, was human radio frequency interference. The 982 MHz frequency is used by various oscillators in electronics, and the specific drift rate observed could be explained by the movement of a human-made source, like a smartphone or a computer near the telescope. The signal's properties, while intriguing, were ultimately just a little too human to be conclusively extraterrestrial. This outcome, while disappointing to some, is a powerful lesson in the scientific process. BLC-1 was not a failure, it was a rigorous test of our methods. It demonstrated that the Breakthrough Listen project's detection and analysis pipelines are incredibly sensitive, capable of finding needles in a cosmic haystack. More importantly, it highlighted the pervasive nature of our own technological footprint. Our planet is now bathed in a leaky bubble of radio signals from countless devices, creating a background hum that SETI astronomers must constantly filter out. The story of BLC-1 is a testament to both our ambition and our humility. It shows that we have the technology to listen, but it also reminds us that the greatest challenge might not be hearing a signal from the stars, but correctly identifying it amid the growing noise of our own world. To truly appreciate the revolutionary nature of fast radio bursts, we must return to the very beginning, to the signal that started it all. Before it was known by a catalog number, it was simply called the Lorimer burst. Its story is one of pure serendipity, a discovery hidden for years in plain sight. The data that held this secret was collected all the way back in 2001 by the iconic Parkes radio telescope in Australia. For 6 years, that data sat in an archive, just another set of observations in the vast library of the universe's radio noise. The telescope was engaged in a survey of the Magellanic Clouds, 2 small galaxies orbiting our Milky Way, and the data was primarily intended for pulsar research. It was a routine scientific endeavor with no expectation of finding something utterly unprecedented. The moment of discovery fell to Duncan Lorimer, an astronomer at West Virginia University, who was working with his undergraduate student David Narkevic. They were sifting through this old Parkes data, not to hunt for mysteries, but to find new pulsars. Their method involved using powerful computer algorithms to search for the telltale, regular pulses of these spinning neutron stars. But one signal refused to fit the pattern. It wasn't a steady, repeating beat. It was a single, colossal spike of energy that lasted for a breathtakingly short 5 milliseconds. To put that in perspective, a snap of your fingers takes about 300 milliseconds. This event was 60 times faster. The signal was so intense and so brief that Lorimer and Narkevic's first reaction was profound skepticism. The most logical explanation seemed to be that it was a glitch, an artifact of human technology, perhaps a burst of interference from a passing satellite, an aircraft's radar, or even a malfunction within the telescope's own electronics. The idea that such a powerful event could originate from deep space was at the time almost unthinkable. What ultimately convinced them they might be looking at something extraordinary were the signal's specific properties. The most crucial clue was its dispersion measure. As radio waves travel across the vast distances of space, they pass through a sparse soup of ionized gas or plasma. This plasma acts like a cosmic prism, slowing down lower-frequency radio waves more than higher-frequency ones. The result is that the higher frequencies arrive at our telescope a fraction of a second before the lower frequencies. The greater the delay or dispersion, the more material the signal has traveled through, indicating a greater distance. The dispersion measure of the Lorimer burst was enormous. It was far too large to be explained by a source within our own galaxy. The only plausible conclusion was that this 5-millisecond flash had journeyed from an incredible distance, likely billions of light-years away, far beyond the Milky Way. This single measurement transformed the signal from a probable glitch into a potential cosmic revolution. To have traveled such a mind-boggling distance and still be detected with such strength meant the energy released at the source was almost beyond comprehension. The Lorimer burst implied an event that, for its brief duration, outshone entire galaxies. When Lorimer and his team published their findings in 2007, the astronomical community was deeply divided. Many respected scientists were openly skeptical, arguing that such a phenomenon defied known physics. They proposed alternative explanations, from terrestrial interference to rare atmospheric events. For several years, the Lorimer burst remained an intriguing but unproven anomaly, a ghost in the data that many were hesitant to believe in. Its ultimate validation came not from argument but from repetition. The turning point was the gradual discovery of other, similar signals by different telescopes around the world. When the Arecibo telescope in Puerto Rico detected a burst with similar characteristics in 2012, followed by more from the Green Bank telescope and others, the doubt began to dissolve. The Lorimer burst was no longer a solitary oddity. It was the first identified member of an entirely new class of astrophysical phenomena. It forced the scientific community to confront a stark reality. The universe was capable of producing transient events of unimaginable power that previous theories had not predicted. This one signal, found by accident in old data, single-handedly created the field of fast radio burst research. It pushed scientists to conceive of new high-energy processes, from the mergers of ultra-dense objects to the eruptions of magnetars, fundamentally expanding our understanding of cosmic violence and proving that the universe still holds colossal surprises. But while projects like Breakthrough listen deploy vast resources, some of the most intriguing signals have been found through the power of the crowd. In the early 2000s, millions of people around the world volunteered their personal computers to join a revolutionary experiment called SETI at home. Instead of relying on a single supercomputer, the project cleverly divided massive amounts of radio telescope data into tiny chunks, sending them out to volunteers' machines to analyze during their idle processing time. Your screensaver could be searching for aliens. It was a stunning demonstration of collective effort, and in 2003, this distributed network flagged something peculiar, a signal that came to be known as SHB-02+14a. This signal possessed a fascinating combination of traits that made it a compelling candidate, at least initially. It was detected not just once, but on 3 separate occasions, each time centered on a frequency of around 1420 MHz. As with the WOW signal, this is the resonant frequency of neutral hydrogen, the most common element in the universe, making it a prime candidate for an intentional interstellar broadcast. Furthermore, the signal exhibited a slight drift in frequency, a shift consistent with what you would expect if the transmitter were located on a planet orbiting a distant star. For a community of volunteers who had spent years hoping their screensaver might find a needle in a cosmic haystack, this was a moment of electrifying possibility. The most puzzling aspect of SHB-02+14a, however, was its apparent point of origin. When astronomers traced its coordinates, they found it emanating from a seemingly empty patch of sky between the constellations Pisces and Aries. There was no known star system, no visible galaxy, nothing of obvious interest within 100 light-years of the calculated location. It was as if the signal was coming from the void itself. This emptiness fueled speculation. Could it be from a spaceship in transit, or a civilization so advanced it had built a transmitter floating in the deep darkness between stars? The mystery was as deep as space itself. Ultimately, the signal's initial promise faded under the harsh light of scientific scrutiny. The primary issue was its extreme weakness. SHB-02+14a was a very faint signal, hovering right at the edge of detectability. Its strength was so low that it was impossible to rule out the possibility that it was merely random noise, a statistical fluke amplified by the immense volume of data being processed. The fact that it was only observed 3 times and never again by more powerful, targeted observations made verification impossible. Without a stronger, repeatable signal, it could not graduate from an intriguing anomaly to a confirmed discovery. The story of SHB-02+14a serves as a crucial lesson in the challenges and realities of citizen science SETI. It highlighted the delicate balance between sensitivity and false alarms. The SETI at Home project was brilliantly designed to catch incredibly faint whispers that might be missed by other methods, but this very sensitivity also meant it was highly susceptible to picking up insignificant noise that merely looked like a signal. The case demonstrated that while distributed computing can generate exciting candidates, the final, definitive confirmation still requires the focused power of large, professional radio telescopes. It's a testament to the patience of science, reminding us that the road to a potential discovery is often paved with intriguing, but ultimately unverifiable clues. Sometimes the most profound signals from the universe aren't heard but seen. They arrive not as a burst of radio waves, but as a flicker of starlight, a subtle dimming that hints at something vast and strange moving through the cosmos. This brings us to one of the most compelling mysteries of the 21st century, a star that needed no radio telescope to capture our imagination, only a patient eye watching for shadows. Known officially as KIC 8462852, but immortalized as Tabby's star after the astronomer Tabitha Boyajian, who led its investigation. This object presented a puzzle so bizarre it forced scientists to reconsider the very limits of what might be possible. The discovery was made by the Kepler Space Telescope, a remarkable observatory designed for one primary purpose: to find planets beyond our solar system by staring unblinkingly at a single patch of sky, monitoring the brightness of over 150,000 stars. Kepler hunted for the telltale sign of a transit, the tiny, periodic dip in a star's light that occurs when an orbiting planet passes in front of it. These dips are usually small, predictable, and symmetrical. A Jupiter-sized planet, for instance, might cause its star to dim by only about 1%, and it does so like clockwork every orbit. But Tabby's star refused to follow the rules. The data from Kepler revealed not gentle, repeating dips, but chaotic, dramatic plunges in brightness. The star's light would sometimes drop by a staggering 20%, an amount that would require an object far larger than any planet to block its light. Even more strangely, these dimming events were wildly irregular. Some lasted for days, others for weeks, with no discernible pattern. It was as if something massive and utterly unlike a planet was sporadically drifting in front of the star. When natural explanations seemed insufficient, the human mind raced toward the extraordinary. The most tantalizing and admittedly wild hypothesis was that we were witnessing the construction of an alien megastructure. Specifically, scientists like Jason Wright of Penn State University suggested the dimming could be caused by a Dyson swarm, a vast collection of energy-capturing satellites or panels orbiting a star, constructed by an advanced civilization to harness its total power output. Such a structure would not be a solid shell, but a chaotic, uneven swarm, perfectly accounting for the irregular and deep dimming patterns observed. This idea, while extreme, was not entirely unscientific. It was a testable hypothesis born from a simple question. If an advanced civilization did build such a thing, what would it look like from light years away? The answer, remarkably, fit the data from Tabby's star surprisingly well, catapulting this distant sun from an astronomical curiosity to a global sensation. Of course, extraordinary claims require extraordinary evidence, and the scientific community embarked on a rigorous campaign to find more natural explanations. The leading theory soon became one involving colossal amounts of cosmic dust. Observations from other telescopes, including the Spitzer Space Telescope and ground-based observatories, revealed that the dimming was more pronounced at certain wavelengths, particularly in blue light compared to infrared. This spectral fingerprint strongly pointed toward dust as the culprit. Fine particles of dust, perhaps from a massive family of comets shattered by a gravitational disturbance or from a recent planetary collision, could create a complex, uneven cloud that would cause exactly the kind of irregular dimming seen. Other hypotheses suggested intrinsic variability of the star itself, or the presence of a large, distorted ringed object like a giant planet with immense, dusty rings. Over time, as more data was collected, the alien megastructure hypothesis lost favor to these more natural, albeit still highly unusual, scenarios. Yet, the true legacy of Tabby's star is far greater than solving a single mystery. It fundamentally changed the way we approach the search for intelligence in the cosmos. It demonstrated that a technosignature, a sign of technology, might not be a deliberate radio message, but an unintended byproduct of colossal engineering on a scale we can barely imagine. The star became a powerful catalyst, moving the search for extraterrestrial intelligence beyond just listening for signals, and into the realm of looking for massive alterations to a cosmic environment. It challenged astronomers to broaden their definition of what constitutes a signal, opening up an entirely new frontier in astrobiology where the very architecture of a star system could be the message. In the end, whether the culprit was a swarm of comets or something else entirely, Tabby's star taught us that the universe is capable of producing phenomena so strange they blur the line between natural wonder and artificial creation. forever expanding our sense of cosmic possibility. Just when astronomers thought they had a handle on the bewildering nature of fast radio bursts, the universe, or perhaps something much closer to home, decided to play a trick on them. For years, a separate class of mysterious signals began appearing in the data, signals that seemed to mock the very characteristics scientists were trying to understand. They were named Puritans, after a mythical winged stag that casts a human shadow, a fitting name for signals that looked cosmic but were, in fact, something far more mundane. Puritans were the ultimate imposters. Like genuine fast radio bursts, they appeared as short, intense blips of radio energy, but they possessed a crucial, telltale difference that initially went unnoticed. While a true cosmic signal arrives from a specific point in space and can only be detected by a telescope pointed directly at it, Puritans had a bizarre property. They were seen simultaneously by multiple receivers of the radio telescope, even those aimed in completely different directions. This was a major clue that their origin was not a distant point in the cosmos, but a local, diffuse source flooding the entire area with radio noise. For a long time, this distinction was subtle enough that Puritans created significant confusion, muddying the waters of fast radio burst research and leading to cautious skepticism about every new detection. Were scientists studying a new astrophysical phenomenon, or were they just cataloging a strange form of terrestrial interference? The prime hunting ground for these perplexing signals was once again the Parkes Radio Telescope in Australia. The observatory seemed to be a magnet for cosmic mysteries, but the Puritans were a particular nuisance. They would appear sporadically, frustrating astronomers who couldn't pinpoint their source. The investigation took on the qualities of a detective story. Researchers meticulously analyzed the timing of the signals, looking for patterns. They checked for correlations with weather events, solar activity, and even air traffic. They considered everything from atmospheric phenomena to secret military experiments. Yet, the origin of the Puritans remained stubbornly elusive, a ghost in the machine that was haunting one of the world's premier astronomical facilities. The breakthrough finally came in 2015, and the solution was as hilarious as it was humble. A team of scientists decided to install a radio monitor at the observatory site itself, an instrument designed to listen for any local radio emissions that might be interfering with the telescope's delicate work. It wasn't long before the monitor picked up a familiar signal, a Puritan. The team then traced the emission to its source, and the culprit was revealed: a microwave oven in the observatory's staff kitchen. The mystery was solved. The Puritans were not messages from the edge of the universe. They were the result of hungry astronomers and impatient staff members. The specific mechanism was brilliantly simple. When a microwave oven is running, it contains the radiation within a sealed metal box. But if you interrupt the cooking process by opening the door before the timer has finished and the magnetron has fully switched off, a brief burst of radio waves can escape. At the precise moment the door's safety latch was disengaged, a tiny pulse of radiation would leak out. This pulse, though faint to human senses, was a roaring shout to the incredibly sensitive Parkes telescope sitting just a few hundred meters away. The reason the signals were detected by multiple receivers was because this leaked radiation was bouncing off the observatory's metal structures, filling the entire site with a momentary radio glow. The case was closed not with a complex astrophysical theory, but with a simple sign on the microwave: "Do not open before timer ends." The story of the Puritans is far from just a humorous anecdote. It serves as a critically important lesson in the rigorous process of science, especially in a field where the signals being hunted are often weaker than the background noise of our own civilization. It underscores the immense challenge of distinguishing a true cosmic event from the countless artificial signals that permeate our modern world. The resolution of the Puritan mystery actually gave astronomers more confidence in the reality of fast radio bursts. By definitively identifying and eliminating one source of contamination, they could refine their detection criteria, making their search for genuine cosmic signals cleaner and more reliable. It's a testament to scientific perseverance and humility, showing that sometimes the greatest discoveries are not about finding something new in the heavens, but about correctly identifying what has been right under our noses all along. While our search for signals often reaches for the distant galaxies, some of the most powerful and enigmatic transmissions originate right in our own cosmic backyard. The planet Saturn, with its magnificent rings, has long been a subject of awe, but it also produces a different kind of spectacle, an invisible orchestra of intense radio waves. These aren't whispers from the void, they are the roaring soundtrack of a giant planet's magnetic field in action. For decades, we could only theorize about this cosmic radio station, but the Cassini spacecraft, which spent 13 years orbiting Saturn, gave us a front-row seat to the show. What it heard when converted into sound waves we can perceive is a chorus of eerie shrieks and bursts that sound less like a natural phenomenon and more like the haunting cries of space ghosts. The source of this otherworldly noise is a fascinating cosmic interaction. Saturn possesses an immensely powerful magnetic field, a vast, invisible bubble that extends far out into space. This magnetic environment is not a quiet vacuum. It's a dynamic arena where charged particles from the Sun and from Saturn itself get caught and accelerated to incredible speeds. But the real conductor of this radio orchestra is one of Saturn's small, icy moons, Enceladus. This unassuming world is now known to be geologically active, with massive plumes of water vapor and ice crystals erupting from its south pole like giant geysers. These plumes constantly feed particles into space, creating a torus, or a donut-shaped cloud, of material that follows Enceladus's orbit around Saturn. As these particles become ensnared by Saturn's magnetic field, they are funneled down toward the planet's poles, and this immense flow of energy generates powerful radio emissions known as Saturn kilometric radiation. The Cassini spacecraft was equipped with a radio and plasma wave science instrument specifically designed to detect these kinds of signals. The data it sent back was a complex stream of numbers representing radio wave intensity and frequency. To make this data accessible to human senses, scientists at NASA performed a simple but profound conversion. They translated the frequencies and intensities into audio waves. The result is deeply unsettling. You hear crackling static that suddenly erupts into sharp, rising whistles and dramatic, sweeping whooshes. These sounds are not literally traveling through the vacuum of space. Instead, they are a sonification, an auditory representation of the intense energy processes happening around Saturn. If you are floating near the planet's poles with a radio receiver, this is exactly what you would hear, a constant, shrieking storm of natural radio energy, a reminder that even within our solar system, the cosmos is far from silent. This research does much more than just satisfy our curiosity about the sounds of other worlds. It plays a critical role in a much larger scientific endeavor, the search for truly anomalous signals. By meticulously studying and understanding the complex radio signatures produced by known natural phenomena like Saturn's magnetic interactions, scientists can create a detailed baseline of what normal cosmic radio emissions sound like. This is akin to a sound engineer learning to identify all the ambient noise in a recording studio. Once you know the hum of the lights, the buzz of the computer, and the rustle of air conditioning, you can far more easily pick out the unique sound of a single instrument, or in this case, a signal that doesn't fit any known pattern. Every time we decode the radio emissions from a planet, a pulsar, or a distant galaxy, we add another filter to our cosmic listening post, improving our ability to distinguish between the universe's natural background music and a potential solo performance that could change everything. The ghostly songs of Saturn are not a mystery to be solved, but a masterclass in understanding the universe's complex vocabulary. Yet the solar system's radio symphony doesn't end with Saturn. Our own neighborhood holds another, even more powerful broadcaster, a planet whose radio shouts are so intense they can outshine the sun in certain frequencies. This brings us to the king of the planets, Jupiter, and its own spectacular display known as the Jupiter radio bursts. These are not faint, hard-to-detect whispers. They are colossal eruptions of radio energy at decametric wavelengths, meaning tens of meters long, that can be picked up by amateur radio enthusiasts with relatively simple equipment right here on Earth. It's a humbling thought. You can build an antenna in your backyard and listen to the real-time interactions between a giant planet and one of its moons, a celestial conversation happening over 400 million miles away. The story of their discovery is a classic example of serendipity in science. In 1955, two astronomers, Bernard Burke and Kenneth Franklin, were using a large radio array in Washington, D.C. to create a precise map of radio sources in the sky. Their goal was to study distant galaxies, but they kept encountering a persistent, unidentified noise that seemed to move against the backdrop of stars. At first, they suspected a glitch, perhaps interference from a nearby piece of farm equipment or a faulty piece of electronics. But as they meticulously tracked the signal, they made a stunning realization. The mysterious radio source was moving in perfect sync with the predicted position of the planet Jupiter. This was a monumental discovery. It marked the very first time radio waves had been detected from another planet, forever changing our understanding of the solar system. We learned that the giant planets are not silent, frozen orbs, but dynamic, energetic worlds with their own powerful electromagnetic personalities. What makes these bursts even more fascinating and complex is that they are not random. Their occurrence is tightly controlled by a seemingly unlikely master, Jupiter's moon Io. This small moon is the most volcanically active body in the entire solar system, its surface dotted with massive volcanoes that constantly spew sulfur dioxide and other particles into space. This continuous eruption creates a tenuous atmosphere around Io, which is constantly being stripped away, forming a torus of ionized gas, a plasma donut that follows the moon's orbit around Jupiter. This is where the cosmic circuit is completed. Jupiter's magnetic field, the strongest of any planet, sweeps through this plasma torus. The interaction generates an immense electrical current, a river of charged particles flowing along magnetic field lines that directly connects Io to Jupiter's upper atmosphere. It's as if an invisible million-ampere electrical cable stretches between the planet and its moon. This powerful current is the engine of the radio bursts. As the charged particles are accelerated along this magnetic highway, they naturally emit radio waves in a process known as cyclotron maser instability. Think of it like a natural planetary-sized particle accelerator. The radio energy is then beamed into space not in all directions, but in a narrow, cone-shaped pattern, much like the focused beam of a lighthouse. For us to detect a burst from Earth, Jupiter must be positioned so that this rotating radio beacon briefly sweeps across our planet. This explains why the bursts are sporadic and why their timing depends precisely on the orbital position of Io. It's a three-body dance involving Jupiter's rotation, Io's orbit, and the location of Earth, a celestial clockwork that produces one of the most predictable yet dramatic radio shows in the sky. Beyond their sheer spectacle, the study of Jupiter's radio bursts provides a priceless natural laboratory. They allow scientists to observe in real time the fundamental physics of particle acceleration and magnetic field interactions on a scale impossible to recreate in any lab on Earth. By analyzing these signals, we can learn about the strength and structure of Jupiter's magnetic field, the composition of the particles trapped within it, and the complex ways a planet can interact with its moon. This knowledge is crucial as similar processes are likely occurring around giant planets orbiting other stars. Understanding the radio voice of Jupiter gives us a template for interpreting potential signals from distant exoplanetary systems, teaching us how to listen to the magnetic hearts of worlds far beyond our own. Leaving the familiar radio chorus of our solar system behind, we now turn our attention to a far more distant and enigmatic source, one that seems to defy every attempt at classification. Deep in the heart of our own galaxy, toward the crowded and dynamic center of the Milky Way, astronomers have detected a signal that behaves like nothing else we've ever seen. Officially catalogued under the rather dry name ASCAP J173608 to 321,635, this object has become a focal point of modern astronomy precisely because of its bewildering inconsistency. It's a cosmic will-o'-the-wisp, flickering into existence with no warning and vanishing just as mysteriously, leaving behind a trail of unanswered questions. The discovery was made using the Australian Square Kilometre Array Pathfinder, or ASCAP, a powerful radio telescope designed to map the sky in incredible detail. Over a period of just 9 months in 2019 and 2020, this object was observed a total of 13 times, but it was the nature of these appearances that captured the attention of researchers. The signal didn't just flash on and off like a fast radio burst. Instead, it would slowly brighten over a period of several weeks, becoming a significant source of radio waves, only to gradually fade away over a similar timescale until it was completely undetectable. Then, after a period of silence, it might suddenly brighten again. There was no discernible rhythm or predictable period to this behavior. No clockwork pulse like a neutron star, no regular orbit like a binary system. It was completely erratic, an unpredictable and amorphous glow that seemed to operate on its own inscrutable timetable. When astronomers tried to identify what they were looking at, they hit a brick wall. The first step in solving any cosmic mystery is to compare the new object's properties to known classes of celestial bodies. But ASCAP J173608 to 321,635 matched nothing in the existing catalog. It wasn't a pulsar, as those emit incredibly regular, rapid pulses, and this source was anything but regular. It wasn't a flaring star like a red dwarf, because associated optical or infrared telescopes saw nothing at the same location. It wasn't a microquasar or a gamma-ray burst remnant, as its behavior and emission profile were all wrong. Even when they searched for a possible counterpart using other instruments like the Chandra X-ray Observatory and the Neil Gehrels Swift Observatory, they found absolutely nothing. The object was a ghost, visible only in radio waves and completely invisible across every other part of the electromagnetic spectrum. This made it even more puzzling. Most cosmic objects that vary in brightness do so across multiple wavelengths, but this one was a radio-only phenomenon. The leading hypotheses for what it could be are as fascinating as they are speculative, and they all point toward the existence of a potentially new class of celestial object. One compelling idea is that we might be observing a highly unusual type of stellar remnant, perhaps a magnetar with an extremely long rotation period, or one that is entering a new, previously unobserved phase of activity. Another possibility is that it's a binary system where one object is a compact star, like a white dwarf or neutron star, and it's slowly accreting material from a companion in a very peculiar stop-and-start manner. The most exotic suggestion, however, involves a concept known as a G-object. These are strange, dusty objects that have been discovered orbiting the supermassive black hole at our galaxy's center, which may be bloated stars that have had their outer atmospheres stretched out by tidal forces. Could this radio source be a distant relative of these G objects, acting out its final stages in a bizarre radio performance? What makes ASCAP J173608 to 321,635 so significant is that it represents a frontier of discovery that is becoming increasingly common in astronomy, the unknown unknown. We are no longer just finding new examples of things we already understand. we are stumbling upon phenomena that fall completely outside our established categories. This object is a stark reminder that our galactic center, a region teeming with stars, dust, and a supermassive black hole, is a laboratory of extreme physics that can produce behaviors we haven't even begun to theorize about. Its intermittent, unpredictable nature challenges our methods of observation, demanding patience and a willingness to accept that some of the universe's most intriguing secrets reveal themselves only when they choose to. Yet another signal that momentarily set the scientific world alight arrived in the summer of 2016, this time from a star strikingly similar to our own Sun. The announcement came not through a formal press release, but at a meeting of the International Academy of Astronautics SETI Permanent Committee, a gathering of the world's leading experts in the search for extraterrestrial intelligence. The news was electrifying. A year earlier, on May 15, 2015, the Ratan 600 radio telescope in Zelenchikskaya, Russia, had detected a powerful, narrowband signal from the direction of a star known as HD 164595. Located just 95 light-years away, this star is a near twin of our Sun in terms of its size, age, and composition, and astronomers had already discovered at least one Neptune-sized planet orbiting it. A signal from such a familiar stellar environment, relatively close in galactic terms, made the possibility of a technological origin feel tantalizingly real. What truly captured the imagination, however, was the sheer power implied by the detection. The initial analysis involved a chilling thought experiment. If this signal were an intentional, omnidirectional broadcast from an advanced civilization, a "Hello, we are here" message beamed in all directions like a cosmic lighthouse, the energy required would be almost inconceivable. Calculations suggested it would need to be on the order of 100 billion watts. To generate that much power, a civilization would need to harness the total energy output of its entire star, a feat that corresponds to a Kardashev Type II civilization on the theoretical scale used to gauge a society's technological advancement. This was the stuff of science fiction, a level of engineering that would involve constructs like a Dyson sphere. The idea that we might have just intercepted a leakage signal from such an unimaginably advanced society was both thrilling and humbling. A more plausible, yet still staggering, alternative was also considered. If the signal were not a broadcast in all directions, but a tightly focused beam aimed deliberately at our solar system, the required energy would drop dramatically. In that scenario, the needed power would be more akin to the total energy consumption of our entire human civilization. While still a colossal amount, this placed it within the realm of a Kardashev Type I civilization, one that has mastered the resources of its home planet. This dichotomy between an accidental whisper from a god-like civilization and a deliberate targeted message from a peer framed the intense discussion that followed the announcement. The scientific community, burned by previous false alarms, reacted with a mixture of cautious optimism and rigorous skepticism, immediately calling for follow-up observations. The response was swift and global. Just days after the news broke into the public sphere, the SETI Institute trained its powerful Allen telescope array in California on the star system. The Green Bank Telescope in West Virginia joined the search, along with the Bok Optical SETI Observatory in Panama, which looked for any coordinated flashes of laser light. The result, however, was a profound silence. None of these dedicated instruments detected any trace of the signal. It had vanished as mysteriously as it had appeared. Without a repeat performance, the signal could not be verified, and its credibility quickly waned. The most probable explanation, as is often the case in modern SETI, points back to our own planet. The specific frequency of the signal, 11 GHz, is commonly used by various military and civilian satellites. The leading theory is that the Ratan 600 telescope, with its unique single antenna design, likely intercepted a transmission from a secretive Russian military satellite passing through its field of view. The signal's characteristics, while intriguing, were ultimately consistent with human technology. The episode of the HD 164595 signal, while brief, served as a critical reminder of the immense challenge of distinguishing a cosmic hello from the ever-growing cacophony of our own technological emissions. It underscored the non-negotiable need for rapid verification in SETI, where a candidate signal must be confirmed by multiple, independent telescopes before it can be taken seriously, a process that separates tantalizing possibilities from confirmed discoveries. In the midst of the Cold War space race, a different kind of exploration was quietly taking place at a new radio telescope in Cambridge, England. It was 1967, and a 24-year-old graduate student named Jocelyn Bell Burnell was responsible for analyzing the miles of paper chart recordings that the telescope produced each day. The instrument was designed to study the twinkling of distant quasars, a phenomenon known as interstellar scintillation, and the data was a chaotic scribble of squiggles and lines, most of it meaningless noise. But Bell Burnell possessed a sharp eye and an even sharper mind. She noticed something unusual, a tiny, curious signal that didn't look like anything else. It was a little bit of scruff, as she later described it, a faint pattern that appeared about 1.5 inches along the vast paper trail. What made it stand out was its remarkable regularity. It wasn't a random burst of static, it was a series of pulses perfectly spaced about 1.3 seconds apart. It was so precise it seemed almost artificial. The initial reaction from the research team, which included her supervisor Anthony Hewish, was a mixture of bewilderment and cautious excitement. They named the signal LGM-1, with LGM standing for Little Green Men. It was a tongue-in-cheek label, a half-serious, half-nervous acknowledgement of the incredible possibility they were facing. Could this impossibly regular beat be a beacon? A cosmic navigation signal, or even a message from an advanced civilization? The idea was not completely far-fetched. After all, no known natural object in the universe was known to pulse with such clockwork precision. The signal's rhythm was more accurate than most atomic clocks on Earth at the time. The team had to seriously consider the extraordinary hypothesis that they might have just made the most profound discovery in human history. They kept the finding a closely guarded secret, even refraining from telling the staff at the observatory as they embarked on a tense period of verification, trying to rule out every possible terrestrial or instrumental explanation. The mystery deepened when Bell Burnell, with relentless diligence, discovered 3 more of these pulsing sources in different parts of the sky. This was the critical clue that broke the case wide open. It was astronomically unlikely that 4 separate civilizations would all decide to broadcast on a similar radio frequency with a similar pulsing pattern. The signals had to be natural. The team soon realized they were observing a previously unknown type of celestial object, which they named a pulsar, a portmanteau of pulsating star. The true nature of these objects was a triumph of theoretical physics. They were not stars in the conventional sense, but the incredibly dense, rapidly spinning corpses of massive stars that had died in supernova explosions. A pulsar is a neutron star, a ball of matter so compressed that protons and electrons are crushed together into neutrons. A single sugar cube-sized piece of a neutron star would weigh billions of tons on Earth. The mesmerizing pulse we detect is the result of a cosmic lighthouse effect. A neutron star possesses an immensely powerful magnetic field that is misaligned with its axis of rotation. This field acts like a funnel, accelerating charged particles to near light speeds at the star's magnetic poles. These poles become blazing hotspots that emit intense beams of radiation across the electromagnetic spectrum. As the neutron star spins at dizzying speeds, sometimes hundreds of times per second, these beams sweep through space. Just like the beam from a lighthouse appears as a periodic flash to a distant sailor, the pulsar's beam appears as a regular pulse to our radio telescopes on Earth. We only detect the pulsar if one of those beams happens to sweep across our line of sight. The incredible regularity of the pulse is simply the rotation period of the star itself, a cosmic gyroscope of unmatched stability. The discovery of pulsars, for which Anthony Hewish received the Nobel Prize in Physics in 1974, a controversial omission of Jocelyn Bell Burnell that the scientific community still discusses today, became a cornerstone of modern astrophysics. It provided the first direct evidence for the existence of neutron stars, objects that had been theorized but never observed. It opened up an entirely new field of study, allowing scientists to use these cosmic clocks to test the theory of general relativity, study the structure of the interstellar medium, and even, in the case of the first binary pulsar, provide indirect evidence for the existence of gravitational waves. The story of LGM-1 is a masterclass in the scientific method. It's a journey from a curious bit of scruff on a chart to a world-shaking discovery, a reminder that the universe often speaks in rhythms and patterns, and that sometimes the most profound truths are hidden in the most meticulous analysis of the data. It teaches us that the line between science fiction and scientific breakthrough can be vanishingly thin, and that the greatest discoveries often begin not with a shout, but with a patiently observed, perfectly timed whisper. While many fast radio bursts appear as a single, sharp spike of energy, the universe sometimes delivers a signal with a more complex and revealing structure. Among the many captured by the Parkes telescope, one event from 2015 stands out for its unique fingerprint, and burst officially designated FRB 150815. What made this particular flash, often called the Tara wave after the indigenous Australian name for the local river, so special was its double-peaked profile? Instead of a solitary burst, the data showed two distinct peaks of intense energy arriving just 2.4 milliseconds apart. It was as if the cosmic engine responsible for the explosion had fired off two powerful shots in rapid succession, a detail that provided a crucial new clue for theorists trying to understand what could possibly create such immense power. This double structure is more than just a curious shape. It acts as a timer for the event itself. That tiny gap of 2.4 milliseconds sets a strict limit on the size of the source object. For any single object to produce two separate bursts, the entire event must happen within a region small enough that light can travel across it in a time shorter than the delay between the peaks. This simple principle of physics told astronomers that the engine behind this particular fast radio burst could be no larger than about 700 kilometers across. That's a distance roughly equal to the radius of a neutron star, immediately pointing toward these ultra-dense stellar corpses as the likely culprits. It was a powerful constraint, helping to rule out explanations involving much larger structures or more diffuse events. But the real breakthrough with the Tara wave came from a different kind of analysis, the study of its polarization. When radio waves travel through space, their electric fields can vibrate in a random, disorganized manner, which we call unpolarized light, or they can become neatly aligned. This alignment or polarization is a powerful diagnostic tool. The Parkes telescope's sensitive equipment revealed that the waves of FRB 150815 were highly polarized, and more specifically, they showed a characteristic known as Faraday rotation. As the waves passed through a strong magnetic field on their long journey to Earth, the plane of their polarization was twisted like a screw being turned. The amount of this twisting is directly proportional to the strength of the magnetic field and the density of electrons the signal encountered along the way. Measuring this Faraday rotation gave astronomers a rare glimpse into the environment surrounding the burst source. The data indicated that the signal had traveled through an incredibly magnetized region, an environment with a magnetic field thousands of times stronger than any we can generate in laboratories on Earth. This finding strongly supports the magneta model for at least some fast radio bursts. A magneta is a neutron star with a truly monstrous magnetic field, and a starquake on its surface or a magnetic eruption could easily create the conditions needed to produce both the double-peaked burst and the observed polarization. Each new, well-studied burst like the Tara wave doesn't just add another dot on a map, it adds a piece to a three-dimensional puzzle. The intensity tells us about the energy, the structure hints at the size of the source, and the polarization reveals the invisible magnetic forces at play, helping us to slowly narrow down the list of possible cosmic catastrophes from a wide field of guesses to a select few leading contenders. The story of the signal from HD 164595 is deeply intertwined with the unique instrument that detected it, the Rattan 600 radio telescope. Nestled in the Caucasus Mountains of Russia, this telescope is a marvel of engineering, but it operates on a principle quite different from the large, steerable dishes most people picture. Instead of a single parabolic bowl, the Rattan 600 is a gigantic circular array of nearly 900 rectangular reflecting panels, forming a ring with a diameter of 576 meters. This design makes it exceptionally powerful for scanning a narrow strip of the sky as the Earth rotates, but it also presents distinct challenges for pinpointing the exact source of a signal with the precision of other major observatories. This technical characteristic would become a central point in the debate that followed its most famous detection. The observation itself occurred on May 15, 2015. The telescope was engaged in a broad survey of stellar systems, and the data from HD 164595 showed a strong, narrowband signal at a frequency of 11 GHz. The signal's intensity was what immediately raised eyebrows. It had a signal-to-noise ratio strong enough to stand out from the background static. The team, led by astronomer Nikolai Bursov of the Russian Academy of Sciences, spent over a year analyzing the data, diligently working to rule out all possible terrestrial and instrumental sources before even considering the more extraordinary possibilities. Their internal process was methodical, reflecting a cautious approach despite the signal's thrilling implications. When the news was finally presented at the IAA SETI Permanent Committee meeting in September 2016, it ignited a firestorm of interest but also revealed a stark cultural divide in scientific communication. Unlike many Western institutions, which might have a coordinated press strategy involving peer-reviewed publication and simultaneous public announcement, the Russian team's disclosure was more informal, occurring first within a specialized conference. This approach, while valid within academic circles, allowed the news to leak into the public sphere through blog posts and media reports before a formal paper had been published or a coordinated international verification campaign could be organized. The result was a chaotic blend of legitimate scientific excitement and sensationalist headlines, putting immense pressure on the global SETI community to respond quickly. This pressure catalyzed an impressive, rapid response international effort. Within 24 hours of the news breaking widely, the SETI Institute's Allen Telescope Array in California was pointed toward HD 164595. The Bok Optical SETI Observatory in Panama searched for any coordinated laser pulses. The most comprehensive follow-up came from the Green Bank Telescope in West Virginia, which observed the star system for a total of 5 hours across 2 days, scanning a wide range of frequencies. This global collaboration demonstrated the shared commitment of the SETI community to rigorously test any promising candidate. However, the result from every telescope was the same: utter silence. No trace of the signal was found. The swift and unanimous negative result from other facilities shifted the focus of the investigation away from the star and back toward Earth. A primary hypothesis became one of radio frequency interference, specifically from a secretive Russian military satellite. The 11 GHz frequency is commonly used for satellite downlinks, and the unique design of the Rattan 600, with its fixed circular array, makes it particularly susceptible to picking up signals from objects passing through its wide field of view. A satellite on a specific trajectory could easily have produced a transient signal that appeared to originate from the direction of the star, especially given the telescope's inherent challenges with precise source localization. The cultural context was also a factor. Without access to detailed Russian satellite telemetry, international scientists could not definitively rule out this explanation, which remained the most probable, albeit mundane, conclusion. The episode of the Rattan 600 signal became a case study in the modern challenges of SETI. It highlighted how procedural and cultural differences in scientific reporting can impact the validation process. It underscored the absolute necessity of verification by multiple, independent instruments using different technologies and located around the world. A signal detected by only one telescope, no matter how intriguing, simply cannot be confirmed. This event reinforced a critical protocol in the search for extraterrestrial intelligence: the requirement for immediate and transparent coordination following a candidate detection, a lesson that is now being formally incorporated into international agreements to ensure that the next potential discovery is handled with both the excitement and the rigorous skepticism it deserves. But the search for signals is not limited to sharp bursts of energy or rhythmic pulses. Sometimes the message from the cosmos is written across the entire sky in the faintest of glows. To understand our next enigma, we must tune our instruments not to a specific point, but to the universe's very first light, an afterglow from its infancy known as the cosmic microwave background, or CMB. This is the remnant heat from the Big Bang, a nearly uniform bath of microwave radiation that fills every corner of space, a snapshot of the universe when it was just 380,000 years old. For decades, this cosmic background was seen as the ultimate proof of a homogeneous and isotropic universe, one that is largely the same in every direction. But what if this foundational picture is incomplete? What if, embedded within this ancient light, are subtle clues pointing to a reality far stranger than we ever imagined? This brings us to one of the most profound and controversial discoveries in modern cosmology, a phenomenon dubbed the dark flow. In 2008, a team of astronomers led by Alexander Kashlinsky made an astonishing claim after studying the motion of massive galaxy clusters. By carefully analyzing the CMB light as it passed through these clusters, they could detect a minute shift in its temperature, an effect known as the kinematic Sunyaev-Zeldovich effect. This shift reveals the velocity of the cluster itself. What they found was staggering. It appeared that hundreds of clusters, scattered across billions of light years, were all streaming in the same direction at velocities of nearly 600 miles per second. This wasn't just random motion, it was a coordinated flow, a mysterious cosmic current on a scale so vast it defied conventional explanation. The true enigma of the dark flow lies in its implications. According to the standard model of cosmology, the gravitational pull of matter within our observable universe should be the only force governing the motion of these clusters. But the scale and coherence of this flow suggested an influence from something far beyond the cosmic horizon, from regions of space-time that have been forever separated from us since the Big Bang due to the finite speed of light. It was as if these clusters were being tugged by the gravity of immense structures residing in a realm we can never see. This idea is as revolutionary as it is unsettling, suggesting that our entire observable universe might be just a small part of a much larger, perhaps infinite, structure whose total gravitational pull we can somehow feel. The controversy remains intense, with some researchers questioning the statistical methods or proposing alternative explanations involving subtle instrumental effects. But if confirmed, the dark flow would force a radical rewrite of our cosmic story. The CMB holds other, equally puzzling anomalies. Perhaps the most famous is the so-called axis of evil, a name that reflects how deeply it disturbs our standard models. When scientists created exquisitely detailed maps of the CMB's tiny temperature fluctuations, they expected to see a random, patternless distribution, a celestial fingerprint with no preferred direction. Instead, they found that the fluctuations appear to be aligned along a particular axis in space. It's as if the universe has a preferred direction, a cosmic north that challenges the cornerstone principle of cosmology, the cosmological principle which states that the universe should look roughly the same in all directions. Finding an axis is like discovering that the supposedly smooth surface of a lake actually has a subtle, continent-wide tilt. Other large-scale curiosities add to the mystery. There is a noticeable asymmetry between the two opposite hemispheres of the sky, with one half showing more pronounced temperature variations than the other. There is also a mysterious cold spot, a large, unusually cool region in the CMB that is difficult to explain through known physics. While each of these anomalies could potentially be a statistical fluke or an unaccounted-for foreground effect, their collective presence is deeply suggestive. They hint that our universe might not be as random or as uniform as we have long believed. These aren't signals in the traditional sense of a deliberate message, but they are signals nonetheless, whispers from the fundamental laws of physics, telling us that our current understanding is incomplete. So what could these large-scale mysteries be pointing toward? The explanations venture into the realm of speculative but thrilling physics. One possibility is that these anomalies are cosmic scars, imprints from the instant of the Big Bang itself or even from a time before it. Theories like cosmic inflation, which proposes a period of faster-than-light expansion in the universe's first fraction of a second, could have left a specific pattern on the CMB. The axis of evil, for instance, might be evidence that the inflationary field was not perfectly uniform, creating a slight directional preference that was frozen into the fabric of spacetime. Even more radically, some physicists suggest these patterns could be evidence of a collision with another universe in a vast multiverse, a cosmic bruise left by a neighboring bubble universe in the infinite foam of creation. The investigation of the CMB is a testament to our relentless pursuit of deeper knowledge. We are now entering an era of next-generation observatories like the Simons Observatory and the upcoming LightBird satellite, which are designed to measure the polarization of the CMB with unprecedented precision. These missions will search for the faint imprint of primordial gravitational waves, ripples in spacetime from the Big Bang, and they will also scrutinize these anomalies with a clarity we've never had before. They will test whether these strange signals are mere illusions or the first glimpses of a grander cosmic architecture. The ancient light of the cosmic microwave background, once thought to be the final chapter in the story of the Big Bang, has instead become a new beginning, a Rosetta Stone for deciphering the universe's deepest secrets and perhaps for reading the first signals from a reality that lies beyond our own. For all our sophisticated telescopes listening to the symphony of light, we have long been deaf to a different kind of cosmic messenger, one that travels straight through matter as if it weren't even there. These are neutrinos, the ghost particles of the universe, and their story takes us to the most desolate place on Earth in pursuit of the most violent events in the cosmos. Buried deep within the Antarctic ice, the Ice Cube Neutrino Observatory is not a telescope in any conventional sense. It consists of over 5,000 optical sensors embedded in a cubic kilometer of pristine ice, waiting for a vanishingly rare interaction. The entire setup functions as a gigantic trap, designed to catch the fleeting signature of a single high-energy neutrino colliding with an atom in the ice. For years, IceCube detected these cosmic ghosts, but they arrived from random directions in the sky, their origins a complete mystery. They were signals without a source, whispers in the dark with no identifiable speaker. That all changed dramatically in September 2017. On the 22nd of that month, IceCube's sensors recorded something extraordinary, a single neutrino with an energy of about 290 tera-electronvolts. This was no ordinary ghost. It was a heavyweight carrying the energy of a well-thrown baseball, but compressed into a subatomic particle smaller than an atom. Such immense energy meant it had to be the product of a truly cataclysmic event, a cosmic particle accelerator of almost unimaginable power. Most importantly, for the first time, IceCube could trace its path back to a specific patch of sky with a precision sharp enough to point other telescopes in the right direction. An automated alert was sent out to observatories around the world, and within moments, the entire astronomical community turned its eyes and its other instruments toward the coordinates. What they found was a celestial beast already in a state of eruption. The source was a galaxy known as TXS 0506+056, located about 4 billion light-years away. At its heart lies a supermassive black hole, billions of times the mass of our Sun. But this isn't a quiet monster, it is a blazar, meaning one of its powerful jets of radiation and particles is pointed directly at Earth. Observations from the Fermi Gamma Ray Space Telescope and others revealed that this blazar was in the midst of a tremendous flare, shining brilliantly in high-energy gamma rays. The timing was perfect. The neutrino had arrived just as the blazar's activity peaked. This was no coincidence, it was a correlation that marked a historic breakthrough. For the first time, humanity had identified a definite source of high-energy cosmic neutrinos. This event, known as IceCube 170922a, ushered in a new era of astronomy called multi-messenger astrophysics. For centuries, we have studied the universe through light, the electromagnetic messenger, but light can be blocked, scattered, or absorbed by dust and gas. Neutrinos, on the other hand, are elementary particles with no electric charge and almost no mass. They barely interact with anything, flying in a straight line from their source, unaffected by magnetic fields or interstellar material. By combining the neutrino signal, the particle messenger, with the gamma-ray light, astronomers could do more than just identify the source. They could begin to understand the brutal physics happening within that jet. The detection confirmed a long-held theory that the relativistic jets from blazars are capable of accelerating protons to nearly the speed of light. When these ultra-fast protons collide with other particles near the black hole, they can produce both gamma rays and, as a byproduct, the high-energy neutrinos that IceCube detected. The implications of this single ghostly signal are profound. It provided the first compelling evidence pinpointing blazars as origins for some of the universe's most energetic cosmic rays, which are mostly protons and atomic nuclei that constantly bombard Earth. For a century, the source of the most energetic cosmic rays has been one of astronomy's greatest puzzles. The detection from TXS 0506+056 offered a crucial piece of the puzzle, revealing that these enigmatic particles are forged in the intense fires of supermassive black holes. It demonstrated that the universe doesn't just communicate through light. It sends us tangible pieces of its most extreme environments, particles we can catch and study. This landmark event transformed neutrinos from passive phantoms into active guides, opening a ghostly window onto the violent engines that shape the cosmos and proving that sometimes the most revealing signals are the ones that pass through everything to deliver their message directly to us. Just when we think we have categorized the cosmos, it presents us with a new class of object so bizarre it defies all existing labels. The story of the strange radio circles, or ORC, begins not with a decades-old archive, but with a cutting-edge telescope mapping the sky in real time. The Australian Square Kilometre Array Pathfinder, ASCAP, is a revolutionary instrument composed of 36 identical dish antennas working together as a single super telescope. Its mission is to conduct a vast and sensitive survey of the entire southern sky in radio waves, and in 2019, it started delivering data of unprecedented clarity. It was during this survey that astronomers noticed something they had never seen before: faint, ghostly circles of radio emission hanging in space like cosmic smoke rings. They were so unusual that the team initially dismissed them as image processing artifacts, glitches created by their own software, but the circles persisted. When they were confirmed as real celestial objects, the researchers, with a touch of humor, gave them a name that perfectly captured their essence: odd radio circles, or ORC. The defining characteristic of these circles is their sheer scale. They are colossal structures with diameters spanning hundreds of thousands of light years, making each one larger than our entire Milky Way galaxy. Yet, despite their immense size, they are incredibly faint and are completely invisible to telescopes that observe in optical, infrared, or X-ray light. They are ghosts in the radio spectrum, visible only to the most sensitive radio eyes like ASCAP. Adding to the mystery, most of them contain a bright galaxy at their very center, like a jewel set in a vast circular band. This central positioning is unlikely to be a coincidence, strongly suggesting that the galaxy is the source, or at least the catalyst, for the strange phenomenon surrounding it. But what kind of event, originating from a single galaxy, could create an enormous symmetrical structure on an intergalactic scale? The known universe offered no ready answer. Astronomers have scrambled to develop theories, and the leading ideas are as fascinating as the objects themselves. One compelling hypothesis suggests that ORCs are the aftermath of a titanic explosion at the heart of the central galaxy. Imagine two supermassive black holes, each weighing billions of suns, finally merging after a long gravitational dance. The collision would send a cataclysmic shockwave of energy blasting outwards through intergalactic space at a significant fraction of the speed of light. This shockwave would accelerate electrons, causing them to emit synchrotron radiation, the same type of emission that lights up the remnants of supernova explosions, but on a scale millions of times larger. The resulting expanding shell would appear to us as a perfect or nearly perfect circle. This explanation elegantly ties the ORC to a known, if extreme, astrophysical event, painting it as the largest known example of a cosmic shockwave. Another, more speculative theory ventures into the realm of exotic physics, proposing that we might be seeing the throats of wormholes. According to some theoretical models, a wormhole, a hypothetical tunnel through space-time, could have a mouth that appears as a sphere. If such a structure were filled with a plasma of charged particles, it could potentially emit radio waves. From our distant perspective, this sphere would look like a circle. While this idea is certainly a long shot, it demonstrates just how far scientists are willing to go to explain such a perplexing observation. Other proposals suggest these could be the jets of a radio galaxy seen end-on, creating a circular projection, or the result of a starburst galaxy driving an immense spherical outflow of wind. However, each of these theories struggles to explain all of the ORC's observed characteristics perfectly. What makes the discovery of ORCs so thrilling is its immediacy. This isn't a mystery uncovered in old data. It is a frontier of ignorance being exposed live in the current era of astronomical observation. With new radio telescopes like ASCAP and the Cant array in South Africa coming online, we are peering deeper into the radio universe than ever before, and we are finding that it is populated with structures we never knew existed. The ORCs represent a powerful reminder that our maps of the cosmos are still incomplete. Major discoveries are not just relics of the past, they are happening right now, suggesting that the universe still holds enormous surprises, and some of its biggest mysteries are only just beginning to come into focus. Just when the repeating fast radio burst from a distant dwarf galaxy seemed to establish a pattern, the cosmos unveiled a second act that was even more precisely choreographed. Discovered in 2018, FRB 180916.J0158+65, while less of a mouthful, presented a rhythm so regular it felt almost engineered. This wasn't just a source that occasionally decided to burst, it was a cosmic metronome. Astronomers soon realized its eruptions followed a precise 16.35-day cycle. For roughly 4 days, it would fire off multiple bursts, sometimes several per hour. Then, as if a switch had been flipped, it would fall completely silent for the next 12 days before starting the cycle all over again. This wasn't just repetition, it was a predictable clockwork schedule written into the fabric of deep space. The significance of this periodicity cannot be overstated. Such a reliable pattern is a giant clue, strongly suggesting that the source of the bursts is locked in a gravitational dance with another object. The most straightforward explanation is an orbital motion. Imagine a highly magnetized neutron star, a potential engine for these bursts orbiting a companion star. As it travels along its elliptical path, there might be a specific point, perhaps when it is closest to its companion, experiencing intense gravitational or magnetic stresses that triggers the eruptions. The 16-day period would simply be the time it takes for the neutron star to complete one full orbit. This model provides a natural framework for the active and silent phases, elegantly explaining why the bursts only happen during a specific window in the orbital cycle. Another layer of this mystery was peeled back when an international team of scientists achieved a remarkable feat of precision astronomy. Using a network of radio telescopes across Europe known as the European Very Long Baseline Interferometry Network, they pinpointed the location of FRB 180916 with breathtaking accuracy. The signal was not coming from a primitive dwarf galaxy like its famous predecessor, but from a much more familiar environment, a spiral galaxy not unlike our own Milky Way. Even more astonishing was its proximity. This galaxy is located a mere 500 million light-years away, making this repeating FRB one of the closest ever detected. This relative nearness in cosmic terms was a game-changer. It meant the signal was brighter and easier to study in fine detail, allowing astronomers to probe the specific neighborhood where the bursts originate. Zooming into that galactic neighborhood revealed another surprise. The bursts were not coming from the chaotic, star-forming heart of the spiral galaxy. Instead, they were traced to a region on the outskirts, a comparatively quiet suburban arm of the galaxy where massive, short-lived stars are less common. This environmental clue is crucial. It suggests that the system producing these powerful bursts is not necessarily a young, violently active one. It could be a more mature binary system, perhaps containing an older neutron star that is still capable of producing these tremendous outbursts under the right conditions. This finding broadened the scope of potential FRB sources, indicating they can arise in a variety of galactic environments, not just in the extreme stellar nurseries of dwarf galaxies. The combination of a clear orbital period and a precise location in a nearby spiral galaxy makes FRB 180916 a Rosetta Stone for understanding these enigmatic phenomena. It provides a specific, testable model that theorists can now refine. The 16-day cycle rules out extremely short period systems and points toward a companion that could be a massive star, a black hole, or even another neutron star. Each of these possibilities would leave a different imprint on the radio waves, and astronomers are now watching this cosmic clock intently, looking for subtle variations in the bursts that could reveal the nature of the companion. This single, well-behaved repeater has done more than just add to the catalog. It has given scientists a working blueprint, a periodic signal they can observe and decode to finally uncover the mechanics behind one of the universe's most powerful and mysterious voices. But to truly understand the beginning, we must listen for the faintest echoes of creation itself, a whisper from a time when the universe was a simple, dark, and cold place. This brings us to a signal so subtle it wasn't a burst or a pulse, but a deep dip in the cosmic radio background, a signal nicknamed the boomerang for its distinctive shape. The story begins not with a massive dish pointed at stars, but with a small, unassuming antenna in the remote deserts of Western Australia, part of an experiment called EDGES, the experiment to detect the global epoch of reionization signature. Its goal was audacious, to detect the imprint of the very first stars being born, an event that occurred when the universe was a mere infant, only 180 million years after the Big Bang. To grasp why this signal is so revolutionary, we need to picture the early universe. After the Big Bang's initial fireball cooled, the cosmos entered a period known as the Cosmic Dark Ages. For millions of years, the universe was a vast, expanding cloud of neutral hydrogen gas, utterly dark. There were no stars, no galaxies, no sources of light. Then gravity began to pull the densest regions of this gas together, and within these collapsing clouds, the first stars ignited. These were not like the stars of today. They were behemoths, hundreds of times more massive than our sun, burning ferociously and dying young in spectacular supernova. Their birth was the dawn of light, ending the cosmic darkness. The EDGES experiment was designed to hear the echo of that dawn. It wasn't looking for the light from those stars directly. Instead, it was tuned to listen for the effect that starlight had on the hydrogen gas that filled the entire universe. The key lies in a fundamental property of hydrogen. It has a natural resonance, a specific frequency at which it absorbs and emits radio waves, exactly 1,420 megahertz, the same frequency targeted by the WOW signal. As the fierce ultraviolet light from those first stars began to flood the cosmos, it interacted with the pervasive hydrogen gas. The starlight would excite the hydrogen atoms, making them more likely to absorb the background radiation that was also bathing the universe, the cosmic microwave background, the fading ember of the Big Bang. This absorption would create a subtle dip, a small but measurable drop, in the intensity of the background radio noise at that specific hydrogen frequency. Finding this dip would be like finding the fossilized shadow of the first sunrise. In 2018, the EDGES team announced they had found it. Their data, collected over a year, showed a clear absorption profile centered near 78 megahertz. Because the universe has expanded over billions of years, the original signal from the hydrogen line has been stretched or redshifted from its high frequency of 1,420 megahertz down to the lower frequencies we detect today. The location of the dip in the radio spectrum told them when it happened, 180 million years after the Big Bang. It was a monumental claim, seemingly confirming our basic picture of the universe's early history. But there was a problem. The signal was far too deep. The dip was about twice as pronounced as the most optimistic cosmological models had predicted. This unexpected depth is the heart of the mystery and the source of intense controversy. The depth of the absorption dip is a thermometer. It tells us about the temperature difference between the cosmic background radiation and the hydrogen gas. For the dip to be as deep as EDGES observed, the hydrogen gas must have been exceptionally cold, much colder than the models said it should have been at that time. According to standard physics, the only way to cool the hydrogen gas that much would be for it to interact with something even colder. But what could that be? The cosmic microwave background was the dominant heat source, and it was warmer than the gas needed to explain the signal. This left scientists with a stunning possibility. The hydrogen might have been cooled by interacting with something else, something dark and cold. The leading candidate is dark matter. This is where the signal points toward potentially revolutionary new physics. Some theorists propose that in the early universe, neutral hydrogen atoms could have interacted with a form of cool, dark matter particles through a previously unknown force. If these dark matter particles were significantly colder than the ordinary matter, they could have acted as a cosmic refrigerant, sapping heat from the hydrogen gas and cooling it down to the temperatures required by the EDGES data. This idea is as exciting as it is speculative. Dark matter, which makes up about 85% of the matter in the universe, has so far only revealed itself through its gravitational pull. If the EDGES signal is correct, it would provide the first ever non-gravitational evidence for dark matter's existence and properties, opening a window into its nature that has been firmly shut for decades. Of course, such an extraordinary claim has been met with rigorous skepticism. many astronomers question whether the signal is truly cosmic at all. The frequency band Edges was observing is notoriously cluttered with human-made radio frequency interference, and the signal is incredibly faint, buried deep within the noise. Detecting it requires exquisitely precise calibration to subtract the effects of the Earth's ionosphere and the radio glow from our own Milky Way galaxy. Critics argue that an unaccounted-for systematic error in the instrument itself or in the complex data processing could have created the deep dip artificially. Subsequent attempts by other teams using different instruments have so far failed to confirm the signal, leaving the Edges result in a state of tantalizing limbo. Whether the boomerang signal is a genuine message from the cosmic dawn, a fingerprint of dark matter, or a sophisticated instrumental illusion, it perfectly exemplifies the cutting edge of cosmology, where a single, subtle anomaly has the power to challenge our most fundamental understanding of the universe's first chapters. Moving from the clockwork precision of repeating fast radio bursts, we venture into a realm where cosmic violence unfolds on an almost unimaginably vast canvas. Far beyond the explosive death of a single star, the universe hosts collisions between entire families of galaxies, events so powerful they leave behind scars that can be seen across billions of light years. One of the most spectacular of these cosmic scars is known as the Dragonfly Radio Galaxy, a mysterious, wispy structure that, true to its name, bears an uncanny resemblance to the delicate wings of an insect. This is not a single galaxy, but a colossal radio relic, a ghostly imprint of a catastrophic impact that occurred when two galaxy clusters, each containing hundreds or even thousands of galaxies, slammed into one another. To understand the sheer scale of this event, imagine our local group of galaxies, which includes the Milky Way and Andromeda, on a collision course with another similar group. Now multiply that by 1,000. A galaxy cluster is the universe's largest gravitationally bound structure, a bustling metropolis of stars, dark matter, and incredibly hot gas that glows in X-rays. When two of these titanic clusters meet, it is the most energetic event since the Big Bang itself. The actual galaxies, spaced far apart, mostly pass by each other like swarms of bees. But the vast clouds of multimillion-degree gas that fill the space between them cannot avoid a direct collision. This intergalactic gas slams together, creating immense shock waves that ripple outward through the cluster at speeds of thousands of kilometers per second, like cosmic tsunamis. The Dragonfly is one of these shock waves, frozen in time as a gigantic, diffuse arc of radio emission. It is a natural particle accelerator on a cosmic scale. As the shockwave propagates, it compresses magnetic fields and whips charged particles, primarily electrons, to velocities approaching the speed of light. These ultra-relativistic electrons, spiraling along the magnetic field lines, then emit synchrotron radiation, which we detect as radio waves. The delicate, filamentary structure of the Dragonfly is not a solid object. It is a luminous map of these frenetic, high-energy processes, a temporary tattoo on the sky that reveals the passage of a shockwave of almost incomprehensible power. Its fragile appearance belies a ferocious origin. What makes relics like the Dragonfly so valuable to astronomers is that they act as a form of cosmic archaeology. By studying the size, shape, and radio brightness of the relic, scientists can work backwards to reconstruct the details of the collision. They can estimate the speed of the shockwave, the energy released, and even the angle and timing of the impact. It's like arriving at the scene of a car crash and being able to determine the speed of the vehicles by the pattern of shattered glass. These signals allow us to map the history of violence that has shaped the universe's large-scale structure, revealing that the serene tapestry of galaxies we see today is the result of a dynamic and often violent past, a continuous process of buildup through cataclysmic mergers. Furthermore, the presence of a radio relic often tells a more complete story when viewed alongside other observations. In the same cluster, astronomers frequently detect a halo of radio emission at the cluster's center, as well as the brilliant X-ray glow from the hot, compressed gas. By combining the radio data with X-ray observations from space telescopes like Chandra, a detailed picture emerges. The radio relic marks the outward moving shock front, while the X-rays show the distribution of the hot gas that was heated in the collision. This multi-messenger approach transforms the dragonfly from a simple curiosity into a crucial data point for understanding how galaxy clusters, the building blocks of the cosmic web, grow and evolve over billions of years. These faint radio whispers are therefore more than just pretty pictures. They are fundamental tools for measuring energies on a truly cosmic scale, giving us a direct glimpse into the dynamic life and dramatic history of the universe's largest structures. But while collisions on the scale of galaxy clusters reshape the universe over eons, some of the most rhythmic and precise signals come from the very edge of oblivion, from the gravitational maw of a single black hole. Imagine the steady, rhythmic thump of a heartbeat, a sign of life and stability. Now, transpose that image onto one of the most chaotic and destructive environments in the universe, the immediate vicinity of a stellar mass black hole. This is the astonishing reality of a system known as JRS 1915 plus 105, a binary system located roughly 36,000 light-years away, where astronomers have detected a mysterious, persistent X-ray heartbeat that has been ticking with uncanny stability for years on end. The system itself is a classic example of cosmic vampirism. It consists of a regular star and a black hole estimated to be about 14 times the mass of our Sun, locked in a tight gravitational embrace. The black hole's immense gravity is relentlessly pulling gas away from its companion star. This stolen material doesn't fall directly into the black hole. Instead, it forms a swirling, incredibly hot disk of matter called an accretion disk, spiraling inward like water going down a drain. As the gas in this disk is compressed and heated to temperatures of millions of degrees, it glows brilliantly, emitting high-energy X-rays that our space-based telescopes can detect. Most black hole systems exhibit wild, unpredictable fluctuations in their X-ray output as the flow of matter becomes choked or surges violently. But JRS 1915 plus 105 is different. Amidst the chaos, it has displayed a remarkably steady pulse. This pulse is not a simple on-off flash. It is what astronomers call a quasi-periodic oscillation, or QPO. Detected in the X-ray data, this signal is a rhythmic flickering that repeats approximately every 1.85 seconds. While many black holes show fleeting QPOs that come and go over hours or days, the truly extraordinary aspect of this particular heartbeat is its longevity. Observations spanning from the 1990s through to the 2010s, primarily from the Rossi X-ray Timing Explorer and later telescopes, have shown that this oscillation can persist, essentially unchanged for years at a time. This kind of long-term stability so close to a black hole's event horizon, the point of no return, is something theorists had not predicted. It suggests that the chaotic accretion process can, under the right conditions, settle into a surprisingly orderly and durable rhythm. So, what physical mechanism could possibly act as a metronome in such a violent environment? The leading explanation involves a delicate and fascinating balance between two fundamental forces, the inward pull of gravity and the outward push of radiation pressure. As gas spirals inward in the accretion disk, it heats up tremendously, eventually reaching a temperature where the radiation it emits becomes so intense that it actually pushes back on the incoming material. Theorists propose that in this specific system, these forces may have reached a precarious standoff. Imagine a dam that periodically bursts. The inner region of the disk becomes so hot and pressurized that radiation pressure temporarily halts the inward flow of gas, causing it to puff up and block the flow from behind. This buildup of material eventually becomes too much, and a surge of hot gas breaks through the radiation barrier. plunging into the black hole and releasing a tremendous burst of X-rays. The disk then resets and the cycle begins again, creating a regular heartbeat-like pulse. The 1.85-second period likely corresponds to the orbital timescale of matter at the very inner edge of the accretion disk, a region where the fabric of spacetime itself is wildly contorted by the black hole's gravity. This makes the signal far more than just a curiosity. It is a unique and powerful probe of extreme physics. By carefully studying the precise timing and energy spectrum of this heartbeat, scientists can essentially map the conditions in the innermost stable orbit around the black hole, a region where Einstein's theory of general relativity is put to its ultimate test. The stability of the QPO suggests that the black hole's spin is relatively steady, and the properties of the pulse reveal details about the intense magnetic fields and temperatures in this final frontier before the event horizon. It's like having a seismometer on Earth that can detect vibrations. By studying the vibrations of the accretion disk, we can infer the properties of the black hole that is causing them. The persistent heartbeat of JRS 1915 + 105 offers a rare, stable window into the dynamic processes that govern matter under the most extreme conditions imaginable, providing clues that help us understand not just this one system, but the fundamental behavior of black holes throughout the universe. Yet another signal that captured the public's imagination emerged from a star system that seemed almost tailor-made for science fiction. The red dwarf star Gliese 581, located a relatively close 20 light-years away in the constellation Libra, became a household name in the mid-2000s. Astronomers had discovered a family of planets orbiting this small, faint star, and two of them, Gliese 581c and Gliese 581d, were announced to be orbiting within the star's habitable zone, the region where temperatures might allow for liquid water to exist on a planet's surface. The idea of not just one, but two potentially life-friendly worlds right on our cosmic doorstep was an intoxicating prospect, instantly making Gliese 581 the most famous planetary system beyond our own. It was against this backdrop of excitement that a remarkable claim surfaced in 2008. The story broke through an article in the German news magazine Der Spiegel, which reported that astronomers from the University of Geneva, using a telescope in Chile, had detected a mysterious pulse of light, a flash that seemed to originate from the precise direction of the Gliese 581 system. The article suggested the signal was inexplicable and hinted, without stating it outright, at a possible artificial origin. The news spread like wildfire across the internet, fueled by the pre-existing fascination with the system's habitable planets. For a brief moment, it seemed that the long-awaited discovery might have come from the very place everyone was hoping to find it. The reality, however, was far less dramatic and serves as a classic case study in how scientific information can be distorted as it moves into the public sphere. The astronomers involved swiftly and clearly denied the report. They confirmed that they had indeed observed a flash of light, but it was a single, unrepeated event. Their immediate and most logical conclusion was that they had seen the glint of sunlight reflecting off a piece of human-made space debris, perhaps a discarded rocket booster or a defunct satellite tumbling through high orbit. These objects are ubiquitous around Earth, and their random reflections can easily be mistaken for a signal from the stars, especially when a telescope is pointed near the plane of our solar system. There was no hidden data, no secret signal, and certainly no confirmation of anything extraterrestrial. The story was essentially a media-generated myth, but one that gained traction because it aligned so perfectly with our hopes. This episode highlights a critical vulnerability in the modern search for intelligence, the powerful influence of confirmation bias. When we intensely hope to find something, we become predisposed to interpret ambiguous data in a way that supports our desires. The Gliese 581 system was already labeled as a prime candidate for life, so any anomaly associated with it was instantly elevated to the status of a potential message. This psychological tendency can short-circuit the careful, skeptical process that is essential to good science. It demonstrates why the SETI community maintains such strict protocols, requiring that any candidate signal be detected by multiple independent telescopes and be proven to be persistent and clearly non-human in origin before it can be considered a serious contender. The story of the lost signal from Gliese 581 also underscores a deeper, more sobering astronomical revision. In the years following the initial excitement, further studies of the star system have dramatically changed our understanding of its potential for habitability. More precise measurements revealed that the orbits of the planets were different than first thought. It turned out that Planet C, once heralded as a super-Earth in the habitable zone, likely experiences a runaway greenhouse effect, making its surface hotter than Venus. Meanwhile, Planet D, the other hopeful, probably receives too little stellar energy, leaving it a frozen world. The entire concept of a neatly defined, habitable zone around a red dwarf star like Gliese 581 has also been called into question. These stars are notoriously volatile, prone to frequent and powerful flares of ultraviolet radiation that could strip away atmospheres and sterilize the surfaces of any orbiting planets. The system we once imagined as a twin to our own solar system may in fact be a far less welcoming place. Ultimately, the Gliese 581 saga is not a story of failure but one of maturation. It taught the public and the scientific community a valuable lesson about the perils of premature excitement and the importance of rigorous verification. It showed how the journey of discovery is often a process of correction and refinement, where initial, exciting possibilities are tempered by colder, harder data. The case exemplifies the essential cycle of excitement and caution that defines the search for extraterrestrial intelligence. A candidate emerges fueled by hope and intriguing circumstances. It is investigated with intense scrutiny, and it is almost always explained by more mundane phenomena. This cycle is not a discouraging loop but a necessary filtering process, one that ensures that when a signal finally does pass every test, its validation will be built on an unshakable foundation of evidence. The phantom signal from Gliese 581 reminds us that the greatest challenge in listening to the cosmos may be learning to distinguish the voice of our own expectations from the true whisper of the universe. Detecting the faint whisper of the cosmic dawn is arguably one of the most technically daunting challenges ever undertaken in astronomy. The signal itself, a subtle dip in the radio spectrum, is exquisitely fragile. To understand why, picture trying to listen for a single quiet note from a flute being played 100 miles away while standing next to a roaring jet engine. In this analogy, the flute is the ancient hydrogen signal from the early universe, and the jet engine is the cacophonous radio noise generated by our own Milky Way galaxy. This foreground emission, caused by synchrotron radiation from electrons spiraling around galactic magnetic fields, is not just a little louder than the target signal, it is thousands of times more powerful. Isolating the cosmological dip is like trying to measure the depth of a single ripple on the surface of a stormy ocean. The team behind the EDGE's experiment had to become masters of subtraction. Their small, ground-based antenna in the remote Australian outback was chosen specifically for its radio-quiet environment, but even there, the galactic roar was overwhelming. The process is not about detecting the cosmic dawn signal directly. That's impossible with current technology. Instead, it's about building an exquisitely precise model of the foreground noise across a wide range of low-frequency radio waves. Scientists understand the general mathematical shape that this galactic emission should take. They painstakingly measure the total radio power received across many frequencies, and then they subtract their sophisticated model of the foreground. The hope is that what remains after this subtraction is the precious, minuscule signal from the cosmic dawn. It is a high-stakes game of finding a needle in a haystack by meticulously characterizing and removing every single piece of hay. This is where the controversy ignites. Critics of the EDGE's result argue that the claimed detection is so profound that it might actually be too good to be true. The central worry is the potential for unaccounted for systematic errors, subtle flaws in the instrument or in the data processing pipeline that could artificially create a dip that looks exactly like the one being hunted. The antenna and its amplifiers are not perfect. They have their own complex responses to different frequencies and temperatures. A tiny miscalibration, an effect that changes by even a fraction of a percent over the course of a day or a year, could easily imprint a spurious feature into the data that mimics the cosmic signal. Furthermore, the Earth's ionosphere, a layer of the upper atmosphere filled with charged particles, acts like a shifting lens for low-frequency radio waves. Its properties change with the time of day, solar activity, and the seasons. If the model used to correct for the ionosphere's distorting effect is even slightly imperfect, it could leave behind an artifact that perfectly masquerades as the cosmological dip. The debate has spurred a global race for confirmation. Since the EDGE's announcement, other experiments with different designs, such as SARA's in India and LEDA in the United States, have been searching for the same signal. Their goal is not to replicate the EDGE's experiment exactly, but to approach the problem with independent hardware and methodologies, thereby avoiding the same potential systematic pitfalls. So far, these other teams have not confirmed the detection. Some have published results showing a smooth spectrum that contradicts the deep dip found by EDGE's. This lack of independent verification is the strongest argument for caution within the astrophysics community. The scientific standard for a discovery of this magnitude requires that it be confirmed by multiple independent experiments. Until that happens, the EDGE's result remains in a tantalizing limbo, a potentially revolutionary finding that could redefine our understanding of the early universe and dark matter, but one that could also simply be a testament to the incredible difficulty of measuring something that is almost perfectly hidden by the universe itself. The quest to hear the echo of the first stars continues, a meticulous process where extraordinary claims must withstand the relentless scrutiny of independent verification. Now, let's shift our focus from the grand echoes of the Big Bang to a far more subtle, yet equally mysterious signal that permeates the very fabric of our own galaxy. It's a faint, enigmatic glow known as anomalous microwave emission, or AIM. If you could see the sky with microwave eyes, you wouldn't just see the smooth backdrop of the cosmic microwave background, you'd see our Milky Way ablaze with light. Most of this glow comes from well-understood processes, the frenetic motion of electrons in magnetic fields, known as synchrotron radiation, and the gentle warmth emitted by interstellar dust grains. But for decades, a portion of this microwave light stubbornly refused to fit into either category. It was an anomaly, a persistent, diffuse signal with a unique spectral signature that pointed to an entirely new physical process at work on a galactic scale. The mystery of AIM lies in its peculiar characteristics. Unlike the broad emission from hot dust or the distinct profile of synchrotron radiation, this anomalous glow peaks at a very specific range of microwave frequencies between 10 and 60 GHz. It's also strongly correlated with the presence of dense clouds of interstellar dust and gas, the very nurseries where new stars are born. This connection was a vital clue. Whatever was producing this signal had to be incredibly common, spread throughout the galaxy, and intimately linked to the raw materials of star formation. For years, astronomers wrestled with the puzzle, proposing various exotic mechanisms, but none offered a fully satisfactory explanation. The answer, it turns out, might be literally dazzling. The leading theory today suggests that this mysterious microwave glow is coming from the smallest diamonds in the universe. We're not talking about gemstones you could put on a ring. These are nanodiamonds, carbon crystals so tiny that billions of them could fit on the head of a pin. They are thought to form in the turbulent, carbon-rich atmospheres of dying stars and then be blown out into space by stellar winds, seeding the interstellar medium with their microscopic glitter. The revolutionary idea is that these nanodiamonds, when exposed to starlight, can be set spinning at incredible speeds, billions of times per second. This rapid rotation isn't just for show, it has a direct electromagnetic consequence. Because the tiny crystals possess an uneven distribution of electric charge, their frantic spinning causes them to emit radiation precisely in the microwave band, a process known as electric dipole emission. It's a phenomenon akin to how a spinning bar magnet generates radio waves, but scaled down to a molecular level. This elegant explanation accounts for the unique frequency profile of EMI and its association with dusty regions where these nanodiamonds would be expected to form and thrive. While nanodiamonds are a compelling candidate, they are not the only actors in this microscopic cosmic drama. Another leading contender is a class of large, floppy molecules known as polycyclic aromatic hydrocarbons, or PAH. These are essentially soot-like molecules, planar clusters of carbon and hydrogen atoms that are also abundant in space. They, too, can spin and vibrate when energized by starlight, potentially producing microwave emission. The scientific detective work now involves meticulously observing AME in different galactic environments to distinguish between the signatures of spinning diamonds and tumbling PHs. It's a complex forensic investigation, comparing the predicted microwave fingerprints of these molecules against the actual data collected by powerful telescopes. Unraveling this mystery is about more than just identifying a new type of celestial object. It's about completing our inventory of the fundamental building blocks that populate the interstellar medium. The importance of solving the AME puzzle extends far beyond our own galaxy. This faint microwave glow isn't just an academic curiosity. It's a form of pollution, a foreground fog that obscures our view of the most important signal in all of cosmology, the pristine light of the cosmic microwave background. To see the subtle imprints of inflation, the faint gravitational wave patterns, and the other primordial secrets encoded in the CMB, astronomers must create exquisitely clean maps. This requires subtracting every single source of foreground emission, the synchrotron radiation, the interstellar dust, and yes, the anomalous microwave emission. If we don't accurately understand and model the properties of AME, its faint glow can be mistaken for a feature in the CMB itself, leading to profoundly incorrect conclusions about the origin and evolution of the entire universe. By studying these spinning nanodiamonds in our galactic backyard, we are effectively learning how to clean our cosmic lenses, wiping away the local grime to achieve an ever clearer view of the universe's fiery birth. In this way, the most mundane seeming signal, a faint microwave whisper from tiny diamonds, becomes an essential key to unlocking the grandest cosmic mysteries of all. We have journeyed through the whispers of radio telescopes and the flickering of distant starlight, but to conclude our list of 25 enigmatic signals, we must turn to a messenger that is not light at all, but a ripple in the very fabric of reality. On August 17, 2017, the universe did not just send us a signal, it sent us a shockwave. For the first time in history, humanity felt the cosmos tremble. The event, catalogued as GW170817, began when the twin detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, in the United States, along with the Virgo detector in Italy, sensed a distinctive chirp, a rising frequency that lasted for about 100 seconds. This was the unmistakable signature of two incredibly dense objects spiraling toward a final, cataclysmic merger. But unlike the black hole collisions detected before, this signal was different. It was longer, and it originated from a source much closer to home, a relatively nearby 130 million light-years away. More importantly, its characteristics pointed unmistakably to the collision of two neutron stars. Within 2 seconds of the gravitational wave detection, NASA's Fermi Gamma Ray Space Telescope recorded a short, intense burst of gamma rays from the same region of sky. This coincidence was electrifying. For decades, theorists had predicted that the merger of two neutron stars should produce a spectacular flash of gamma rays, but to have both the gravitational wave and the electromagnetic signal arrive almost simultaneously was a confirmation beyond anyone's wildest dreams. It was the starting pistol for the greatest astronomical treasure hunt of the 21st century. An urgent international alert went out, and within hours, dozens of the world's most powerful telescopes from Chile to Hawaii to space swiveled to pinpoint the source. The task was like finding a single specific grain of sand on a beach the size of a continent, but the gravitational wave signal had provided the map. They found it in an unassuming galaxy called NGC 4993, and what they saw was an entirely new kind of cosmic firework. This event was a kilonova, an explosion 1,000 times brighter than a typical nova. As the two neutron stars, each more massive than our Sun but compressed into a city-sized ball, spiraled together and merged, they did not simply form a black hole in silence. They unleashed a cataclysm that reverberated across the entire electromagnetic spectrum. The initial merger created a blistering flash of gamma rays. Then, as a cloud of hot, neutron-rich debris expanded outward, it glowed brilliantly in blue light from the radioactive decay of heavy elements. Within days, that glow shifted to a deep crimson red as heavier elements formed and the cloud cooled. For weeks, radio telescopes continued to monitor the aftermath, watching the fading embers of the explosion. This cascade of signals, the gravitational wave chirp, the gamma ray burst, the visible light, and the radio afterglow, meant that for the first time we were not just seeing the universe, we were hearing it and feeling it. This was the full realization of multi-messenger astronomy, the ability to observe a single cosmic event through multiple independent channels of information. The scientific payoff was nothing short of revolutionary. Perhaps the most profound revelation was the answer to a centuries-old question: where do the heaviest elements in the universe come from? We knew that stars forge elements like carbon and oxygen in their cores, and that the iron in our blood is cast out in supernova explosions. But the origin of elements heavier than iron, like gold, platinum, and uranium, had been a major puzzle. A kilonova provided the definitive answer. The violent environment of a neutron-star merger is a cosmic alchemist's forge. In the ejected debris, neutrons are captured at an incredible rate, building up atomic nuclei into the heaviest elements in the periodic table. The observations from GW 170817 confirmed this spectacularly. Spectrographic analysis of the kilonova's light revealed the unmistakable fingerprints of these heavy elements being synthesized in real time. The calculations were staggering. The single event likely produced an amount of gold and platinum equivalent to several times the mass of our entire planet. This means the wedding ring on your finger or the platinum in a catalytic converter was almost certainly forged in the unimaginable violence of two dead stars colliding billions of years ago. The detection of GW 170817 stands as a landmark in our understanding of the cosmos. It was not merely the detection of another signal, it was the moment multiple lines of cosmic inquiry converged into a single, coherent picture. It confirmed long-standing theories about the origin of short gamma-ray bursts and the nucleosynthesis of heavy elements. It provided a new, direct way to measure the expansion rate of the universe by comparing the distance inferred from the gravitational waves to the redshift of the host galaxy. And most importantly, it cemented a new way of doing astronomy. We are no longer passive observers of light. We are now listeners to the vibrations of space-time and collectors of ghostly particles. This event demonstrated that the universe's most profound secrets are often revealed not through a single messenger, but through a chorus of them, each adding its own unique verse to the story. It is a fitting conclusion to our journey through 25 enigmatic signals, a powerful reminder that the greatest cosmic discoveries often come when we learn to perceive the universe in an entirely new way. From the brief, singular cry of the wow signal to the persistent, rhythmic heartbeat of a black hole's accretion disk, our journey through the cosmos has revealed a universe teeming with voices. We have listened to the explosive screams of fast radio bursts tearing across billions of light years and traced the gentle, spinning glow of nanodiamonds in our own galactic neighborhood. We have felt the very fabric of space-time ripple with the collision of dead stars and puzzled over colossal, ghostly circles that defy explanation. This incredible diversity is the true message. It tells us that the universe is not a silent, static void but a dynamic, evolving entity, communicating through a spectrum of energies and phenomena we are only beginning to decode. Each of these 25 enigmatic signals, whether ultimately explained as a kitchen microwave or a kilonova forge, represents a fundamental victory for human curiosity. The story of the Puritan signal is not one of failure, but a masterclass in scientific humility, proving that the process of questioning and verification is as valuable as the discovery itself. The quest to understand Tabby's star pushed us to consider engineering on a scale we can barely imagine, expanding the very definition of what we should be searching for. And the detection of a single high-energy neutrino from a distant blazar opened an entirely new window onto the cosmos, reminding us that some of the most profound messages are delivered not by light, but by ghostly particles and gravitational tremors. Every mystery, solved or unsolved, acts as a beacon, guiding our technology and our theories toward a deeper, more nuanced understanding of physical reality. The key takeaway from this symphony of the strange is that the greatest exploration is happening not in the void between stars, but within the frontiers of our own knowledge. With every new telescope, every more sensitive detector, and every ingenious method of analysis, we are fine-tuning our ability to listen. We are moving from simply hearing the universe's loudest shouts to discerning its faintest whispers. The subtle dip of the cosmic dawn, the anomalous glow of spinning diamonds, the coordinated drift of dark flow. The silence we once perceived was merely a lack of understanding. We are now learning the language of the cosmos, a language spoken in gravity, magnetism, and light. So, the next time you find yourself looking up at a quiet, star-filled sky, remember that it is anything but silent. It is a vibrant, chaotic, and endlessly creative arena. It holds the potential for a signal that could change everything, a deliberate, unmistakable greeting from another intelligence. But it also holds the certainty of countless other mysteries waiting to be unraveled, each one a puzzle that will push the boundaries of science and redefine our place in the cosmos. The universe is speaking. The question is, what will we hear next? Let us know in the comments which of these 25 enigmatic signals captured your imagination the most, and stay